Hi everyone, this is Jiayang from the University of Melbourne. It is a great honor to be here to present our work, Open World Amodal Appearance Completion. Imagine taking a photo where part of an object is hidden behind another, or watching a video where an interesting object is partly occluded by other elements in the frame. What if we could automatically reconstruct the hidden part of these objects? Then, we can use this complete standalone object in applications like image editing, AR, or even 3D modeling. Ideally, Amodal completion should be able to infer and generate the missing part of any object, regardless of its category or context. However, most traditional methods struggle with this challenge because they're designed for closed-world settings, where object categories are fixed and predefined. This model performs well when dealing with occluded objects within predefined categories, but they fail when faced previously unseen objects in open-world scenarios. In this work, we explore a training-free approach that leverages the extent knowledge embedded in pre-trained large models across different domains, bypassing the need for training on specific occlusion datasets. Let's consider the image shown here. On the left, we see a polar bear hidden by a large ice block. Traditionally, Amodal completion model will struggle with this task unless they were explicitly trained on the polar bears or similar animals. However, our approach enables open-world reasoning about the occluded object, guided by flexible task-based queries. For example, we can prompt the system with "What is the mammal in this image?" or specific category like polar bear. Using just this input and the image, our model can reconstruct the hidden parts of object very well. We design a pipeline that reconstructs the hidden parts of any object without relying on predefined categories. Let's go through this process step by step. First, we take an image as input, and the user provides a test query specifying the object of interest. For example, in this case, the user might use the input squirrel, or they can enter a more abstract query, like "What is the animal?" Our system is designed to handle both specific and abstract description, making it highly flexible. Using this query, we employ a vision language model to generate visible masks, which identify and isolate the part of the target object that can be directly seen in this image. This provides an initial idea, but it only covers the visible regions. To achieve full Amodal completion, we need to predict the hidden parts that are not directly visible. To do this, our data generation pipeline starts by detecting all objects and background segments in the image. We then analyze the occlusion relationship between this segment and the query object. This step is crucial because it helps the system understand which parts of object are missing due to occlusions. However, inpainting the missing regions requires a suitable prompt to guide the reconstruction process. Since our system is built to handle a wider range of natural language queries, we could not assume that the user provided query alone is sufficient for inpainting. Instead, we refine the prompt by combining the test query with the context from image. For example, where the user inputs squirrel, our model might determine that the rodent is a better prompt for guiding the inpainting process. Once we establish occlusion relationships and refine the prompt, we pass both the visible parts and the inferred invisible regions to an inpainting model. The model then iteratively reconstructs the occluded parts, progressively refine the object's shapes and appearance. The final output is a transect RGBA representation, where both visible and previously occluded regions are now reconstructed. The results of human preference studies demonstrate the effectiveness of our approach. As shown in the table, our method achieved the highest overall performance across the entire evaluation dataset. Across all four sources, our approach consistently ranked first. demonstrating the robustness in handling diverse occlusion across open-world scenarios. These figures show visual comparison of our models against existing approach on challenging mutual occlusion scenarios. In the dog and the horse images, which require extensive inpainting, our method is the only one that accurately reconstructs the food body. Other methods struggle to infer the missing region correctly. Similarly, in the book and the Oscar statuette examples, ours achieves the coherent and realistic completions, preserving structural details that other methods miss. Our approach generates high-quality reconstructions that align with human perception. For more details, please scan the QR code to visit our website. Thank you for watching.